Welcome to Matrix Uploaded. My name is Tinyiko Kosa, and of course you see my face and you know it's time for physical sciences, and I inviting everyone grade 10 to 12 at that FET level. You sit down, you learn with me. This lesson takes us from 10 to 12. So we're not leaving anyone out here at Matrix Uploaded, and of course we are uploaded, we're not downloaded, because we give you the best of lessons ever. Now, let's have a look here. Today we're looking at, or we're getting to lesson number 9, and we'll be talking about longitudinal waves and Doppler effect, okay? And like I told you, we're taking it from grade 10 to 12. Okay, now let's have a look at this. What are these longitudinal waves? Okay, now a longitudinal wave is a wave where the particles in a medium move in parallel direction to the direction of propagation. Okay, in other words, if the wave is propagated in that direction, okay, the movement of the particles will be to and fro in this way to show that it is parallel. This is what we mean by parallel. Parallel doesn't necessarily mean in the same direction, but parallel means that it's not at the right angle to each other or at an angle to each other in that way, but parallel, they can never cross. Okay, now a slinky is used to show how longitudinal waves are propagated. So a slinky is that thing there, you would remember something like that. That is, we can use that if you press it from that end there, you press it that way and it is fixed at this end. Then this slinky will begin to vibrate to and fro, and in that way it produces what we call longitudinal waves. Okay. Right, continuing talking about longitudinal waves, the following wave properties will apply to longitudinal waves as well, like we have already started with transverse waves. Okay, we know that with transverse waves we had something called wavelength, lambda. This will also apply to longitudinal waves as well. This frequency, these longitudinal waves also have frequency. They also have amplitude. Okay, right. So all these apply to longitudinal waves as well. Period T, okay, which is how long it takes for one complete vibration to pass a point. Okay, that time there it takes is called the period. And the wave speed V also applies here. Remember, we can use that, or we can use the distance covered by a wave motion divided by the time it took. We can use that. The wave speed applies here. Okay, moving on. Still trying to describe these longitudinal waves here. Remember from the transverse waves, okay, we had the troughs and the crests, okay? But instead of all these things, instead of the crests and troughs, for longitudinal waves we have what we call compressions and rarefactions. Compressions is where that slinky becomes closer here. Okay, so this part here could be a compression where it is compressed a lot. Rarefaction, it would be areas where the slinky, perhaps this one is not a good one. Let me try to have closer one there, and you have got ones apart there. In that way, so that would be a compression. But here to there, you see it is far up, the particles of the slinky are far apart from each other. We have what we call rarefactions. Okay, a compression is a region in a longitudinal wave where the particles are closest to each other. Where the particles are closest to each other, we call that a compression. Okay, and a rarefaction is a region. Rarefaction is a region in a longitudinal wave where the particles are furthest from each other. Okay, like I've already tried to show you with my not so good drawings that I had there. But the wavelength, like we said, all these aspects of waves would apply to longitudinal waves as well. The wavelength is the distance between 2 points, okay, between 2 points that are in phase. So this definition here applies here as well. It doesn't only apply to transverse waves, it applies to longitudinal waves as well. Okay. Amplitude, okay, we have the amplitude here. The amplitude in this case for longitudinal waves will be that maximum displacement of particles of the medium from the equilibrium position. Now you can see that we defining this terminology is pretty much the same because we're talking waves. The only difference here is that we're talking longitudinal waves instead of transverse waves, something we started with earlier on in earlier lessons. Okay, the period. What's a period? This is the time taken for one complete wave motion to pass a point. And remember, this is t. Okay. Next, frequency is the number of complete wave motions passing a point in 1 second. So that is your frequency. And remember, frequency is 1 over t. Okay? Or you can say number of waves, complete waves passing a point in a period of time. Okay? Over a period of time. Right. And wave speed is the distance traveled by wave motion per unit time. We know that. Okay? Now there are sound waves, compressions, rarefactions as compared to to transverse waves in that way. See you in the next section of the lesson.